Ananna. I am a postdoctoral research associate in Professor Ryan Hickox's group at Dartmouth College. And today I will be talking about how we can use the cosmic X-ray background to constrain the growth of black holes over time, as well as the spectral shape of AGN in X-rays. First, let us look at how the form of the AGN spectra in X-rays. The flux from the intrinsic X-ray spectra with respect to energy has a power law form with a high energy cutoff. And this radiation is further reprocessed by reflection from the accretion disk and transmission from the dusty torus. So I'm not going to go into the details of the accretion disk and dusty torus. I'll just say that the obscuring torus, the amount of matter through which we're looking at the AGN is quantified in X-rays in terms of log NH, or how many equivalent hydrogen atoms we're looking through per centimeter square. So let us briefly look at how this obscuration changes this intrinsic radiation. These are physically motivated model spectra of AGN at different obscuration levels. The x-axis here is the photon energy, and the y-axis is the flux from at this photon energy. So these three spectra are unobscured AGN, which is 10 to the power 20 to 10 to the power 22 atoms per centimeter square. If we increase it by 100 times, we go to the quantum thin regime, which is 10 to the power 22 to 10 to the power 24 atoms per centimeter square. And if we increase it 100 times more, we go to the quantum thick regime, which is 10 to the greater than 10 to the power 24 atoms per centimeter square. Now I will show some typical energy windows in which we observe AGN. So this is the soft energy band, which is usually is between 0.5 to 2 keV. This is the hard energy band between 2 to 10 keV. So this is the window in which XMM, Chandra, Rosetta see the universe. This energy window is for new star, which is 3 to 79 keV, and this is for swift path, which is 14 to 195 keV. As you can see, the difference between quantum thin and quantum thick objects is dramatic between these two energy windows. This is why these bands are biased against heavily obscured objects in the local universe. To detect quantum thick objects like this, either we have to go to really low, to really faint fluxes in these bands, or we have to move to higher energy windows such as new star and swift path. So how can we use what we see in X-rays to constrain the growth of AGN over time? We do that using X-ray luminosity functions, which describe the population of AGN at different redshifts, at different intrinsic luminosity and obscuration levels. So my cartoon image of that is, this is how the number density of AGN varies over time, but they are not identical because there are different intrinsic luminosities, and they're also obscured by different levels of matter in between us and the AGN. So these are the three dimensions of X-ray luminosity function: redshift, luminosity, and obscuration. So a correct X-ray luminosity function should be able to consistently reproduce what we see in X-ray surveys in all these different X-ray bands, from swift path, from new star, from Chandra, from XMM. And one of the most important observed constraints is the cosmic X-ray background, which looks like this. So this is what the cosmic X-ray background looks like. It's detected in various energy bands and by different surveys. The x-axis is the energy, the y-axis is the energy flux per solid angle of the sky. At observed energy E, if we add up contribution from all galaxies and all AGN, this is what we get. And this is the galaxy contribution, which is very low. So under 100 keV, we expect that all of this contribution actually comes from AGN. So besides the CXP, another important constraint that we have is AGN number count observed in surveys in different bands. So what is AGN number counts? It is just the number of AGN observed in that energy window. So how many of this AGN do we see per square degree of the sky? So this is what the AGN number counts is. So the x-axis is the flux and the y-axis is just the number we see per square degree. There are many different number counts in different bands and flux limits, and a correct population synthesis model should be able to reproduce all these constraints, and all these data sets are shown here in this table from Ananna et al. 2019. So when we started this work, we were trying to fit all these existing data sets, some of which became available very recently with already existing luminosity functions. So this is all that became available after these luminosity functions were already constrained. And we were unable to fit everything consistently with the already existing luminosity functions. So we formulated a new one using this neural network. So I'm not going to get into the details of the neural network right here, but I can provide details later if someone is interested, and also it's explained in our paper. So let me show you some of the constraints and how well previous luminosity functions fitted it and how well we did. So this is a number of, these are number counts from different surveys in the soft band. One of the deepest data that became available in 2017 is from Chandra Deep Field South 7 megasecond survey. And here you can see this goes deeper than any other survey before. And this is the Weda et al. Fit to it, which was a previous luminosity function, Aird and Buchner. And sorry, and this solid purple line is our work, and it fits all the data here. So this is another constraint, is the new constraint is the Chandra Cosmos Legacy Survey Compton thick number counts from Lanzuzzi et al. 2018. This is the differential number counts. This is the Weda et al. Fit to it, Aird, Buchner, and this is our fit to the data. Another new constraint is the SUVPAT data. And so we have the overall number counts here. It's the Weda, Aird, Buchner fit, and this is our fit to the data. So as you can see, we can our fit goes to all the new available data consistently, and this is our fit to the cosmic X-ray background. So how does our new luminosity function differ from the previous luminosity functions? So this is at intrinsic luminosity at less than 43.6 in the soft in the hard band. So as you can see, our luminosity function is within, it's not identical to any other luminosity function, but it's within the acceptable range, like in agreement with other luminosity function in unabsorbed and Compton thin bands. But it's significantly higher in the Compton thick band. I mean, it agrees with the Buchner et al. One in the low luminosity band. In the high luminosity band, it's higher. So this is just the integrated number of AGN up to a redshift of 0.1, the y-axis, and the x-axis just obscuration. So the main difference is that we have a lot more Compton thick objects than previous luminosity function. And up to a redshift of 0.1, we see that about 50% of all AGN could be Compton thick. So what is the physical implication of such a model? So we constrain the radiative efficiency. We know as matter falls into black holes, some of it is radiated and some of it is accreted into the black hole. Our luminosity function gives us a measure of the fraction that is radiated away. We can integrate over total light emitted over redshift range, and then we can compare it with the measured local black hole mass to find the radiative efficiency. Why should we calculate radiative efficiency? We calculated it because radiative efficiency is tied to one of the fundamental properties of black hole spin. The spin of an AGN affects the intrinsic spectra of the AGN, and therefore we can quantify spin by summing up all the light radiated away by AGN and comparing it with the total mass accumulated by supermassive black holes using Sultan argument. So according to the standard accretion disk model, non-rotating black holes will have a radiative efficiency of 5%, and a maximally rotating black hole will have a radiative efficiency of about 42%. Previous XLF have also calculated the radiative efficiency. What we have done differently, besides constraining a population synthesis model that fits all the X-ray data, is that we have taken into account the full range of errors in conversion from X-ray to bolometric luminosity, which is often done just by a linear factor. So we also considered two different mass densities. So the previous mass density, local black hole mass density was around 400 to 500,000 solar masses per megaparsec cube. A recent correction to this was suggested by Shankar et al., which is around about 4 times lower than previous estimates. So using the previous result, we get a radiative efficiency of around 12%. Using the new value, we get around 34%. So, but this is still a matter of debate of what exactly the local black hole mass density is, and we're going to discuss it a little bit more in a few minutes when we discuss our new black hole mass function. So we also calculated the AGN contribution to total cosmic reionization budget. We do so by converting our external luminosity function to UV luminosity function, again by considering the full range of errors in conversion. We find that our data is in very good agreement with recent UV luminosity functions from Gialongo and Grazia and al. So in this plot, this is the photon density, and this is the redshift, and the y-axis is the redshift. This green and blue lines is the total ionization, total photon density, which you can see that there's a lot of disagreement in what exactly the value is. This orange line are galaxy models that predict how much ionization comes from galaxies. And these black lines here are AGN contribution, and this is the AGN X2 contribution. This is much lower than UV. So these black lines are calculated according to our model, and realistic assumptions about escape fraction give us this result that at most 20% of total reionization contribution comes from AGN. So now that we know the physical implications of our external luminosity function, let us look at what we can say about AGN spectra using CXV. So as I have shown earlier, the photon flux from AGN follow this power law form with respect to energy. While defining the spectra of underlying AGN population, most population synthesis models assume a distribution in these parameters rather than one single value. So a distribution in the like gamma, the photon index, and cutoff energy. When formulating our population synthesis model, we assume distribution in all the parameters. However, we realize that there's a lot of uncertainty within observed samples, and here we present some examples of the discrepancy. Okay, so here we present some observed samples. So there's a disagreement, for example, in cutoff energy. And even though the difference between 1.96 and 1.72 doesn't seem like a lot, if you look at this intrinsic spectra, if we decrease this gamma too much and increase the cutoff too much, both of these causes the flux to drop at a lower rate with increasing energy, adding too many photons at high energy end. And then no matter what space density of AGN we end up using, the spectra does not add up to produce the necessary shape of the CXV. So it's going to become constant at this point. So it's not going to drop fast enough to reproduce this shape. So there are some gaps in our understanding. XLFs produce vastly different results with different spectral assumptions when we try to produce what we observe in different surveys. Observed AGN samples do not agree on average X-ray spectral parameters, probably due to differences in selections, and it is also difficult to get enough photon counts to constrain AGN spectra. Constraining certain parameters such as cutoff energy is easier if the value of the cutoff energy is low, if it is, because we have very few photons in high energy. So there's also a biases on what we can even constrain. But since we know that the CXV cannot be fitted by just any parameter combination, can we use that information to constrain the parameter space of AGN? Gili et al. 2007 also reported similar results, where they found that they are unable to produce any luminosity function which can reproduce the CXV if they assume a high dispersion in the photon index in gamma, and also a high cutoff energy simultaneously. We did a comprehensive exploration using our neural network to constrain the entire AGN parameter space and rule out parts which could never fit the CXV. We ran our neural network for the entirety of the observed parameter space and produced a probability distribution of how well each region fits the CXV. This tool is actually, this neural network is available to be run online. And the link is provided in Ananna et al. 2020A. So the input parameter for this tool are the photon index gamma and the dispersion in gamma, the reflection scaling factor R, the dispersion in R, and the high energy cutoff E, and dispersion in E. Here is an example of how the parameter space is ruled out. Sorry. Here is a snapshot of the acceptable parameter space when we assume the same parameters for all absorption bins. So the x-axis in each of these subplots is the average cutoff energy, and the y-axis is the photon index. And the subplots from left to right show increasing dispersion in photon index, and from top to bottom, it shows increase in the reflection scaling factor. And you can see this is the 1 sigma acceptable region, the 2 sigma, and the 3 sigma acceptable region. And this region can be completely ruled out according to analysis. It never fits the CXP. But the user of the online tool can explore a lot more than the parameter space shown here using this Jupyter notebook that anybody can use. You can specify the photon index, the reflection scaling factor, the cutoff energy, and see which area fits the CXP. And we don't need to assume that all, for example, many surveys find different parameter spaces for different level of obscuration. So the tool can accommodate that, and you can choose different parameter spaces for different level of obscuration. So this is for unobserved AGN. You can specify different parameter space for competent thin and then competent thick AGN. And the tool tries to fit the CXP, find the best possible fit to CXP by varying the underlying AGN population. And then it gives us the chi-square value and the p-value for the level of fit for each data set. So you can see that if it can be ruled out with respect to the CXP. So the overall conclusions from this work about the CXP is that we require about 50% of agent to be competent thick within a ratio of 0.1, and then higher radiative efficiency. We find higher radiative efficiency than previous work, and then AGN can contribute up to 20% of the cosmic reionization budget. And we can, at most, we can place strong constraints on agent spectral parameters using the CXP. So we are currently working on BAS, black hole mass function and integration distribution function. And because of the SwiftBAT selection function, we constrain the first type 2 AGN black hole mass function as well as type 1. And we have some interesting results coming up, and we hope to submit that within a month or two. We find that type 2 AGN have higher Eddington ratios. Type 2 AGN have lower Eddington, lower number density of Eddington ratio at high lambdas, and the black hole mass functions are more or less consistent for type 1 and type 2. So we have some exciting results coming up. Thank you very much.